Well, good morning. We are going to continue our discussion of stability. Last time we talked about stability, different mechanisms, different criteria for stability, and one that we in particular derived in the last lecture was the Nyquist stability criterion. So the idea here was that if you, and we did the derivation, so the idea was that if you start off with a system that has a loop gain of, let's say Ts, that is the system that has a loop gain, that open loop is stable, then the question is that once you close the loop with this open loop stable system, how do you determine whether or not it's stable? And one of the things that we saw that there were two different ways to look at this. We looked at the Bode plot view, which basically was looking at the magnitude and phase of the loop gain, T of j omega. And then we saw that you can basically see it as a versus as a function of omega. This is usually log of omega. And we have a plot like this. But now we saw that if you look at the real and imaginary part of it, in essence, do a polar plot of this magnitude and phase. So the Nyquist criterion was basically is a visual criterion that deals with the real part of T of j omega and the imaginary part on the y-axis, which produces a polar plot of this, where this is the magnitude and that's the phase of the polar plot. So this is essentially, if you have a point here, this is the magnitude of the loop gain, and this is the phase of the loop gain. So now if you take that plot and convert it to a plot like this, what happens is that you start off with something around here, because you start off with something that has at zero frequencies, at zero omega, you have zero phase, and some larger magnitude for a low pass system like that, and gradually the magnitude drops and the phase goes to some value. So in this case it goes through here, and eventually the magnitude at omega infinity goes to 0. So this was omega 0 and this was omega infinity. And this was basically the basic polar plot representation of this thing. But the criterion that we developed last time was that it's really the point -1 on the j omega axis, on the real axis, that matters. So, and we saw that the criterion boiled down through a derivation to whether or not you encircle this. And the number of encirclements of this thing is going to give you, in a linear system, will give you the number of right half plane pole if you assume that your original open loop system doesn't have any right half plane poles. So here what happens is that, so in this case there's no encirclement. And the way we usually do the polar plots is we usually look at it from 0 to omega plus infinity, but we saw that in the derivation it actually starts from negative infinity to positive infinity. So if you really want to think about it, you have to start thinking about the other half of the plot, which is often not shown. So there's an other half to this plot which starts from negative omega infinity, which is the mirror image of this with respect to the x-axis. It goes up as from negative infinity, goes to omega 0, and then continues on to omega plus infinity. So this should be symmetrical, the top and bottom part of it. And that's why we don't show. So in this case, and the criterion for encirclement is that if you sit at the point -1, right, and then you look at it, how many turns you have, how many full real turns you have by the end of the cycle. So in other words, in this case, you can think about, one way to think about it is that you can have like a little string or a little kind of rubber band. And at the end of the process, when you start from one point and end up at that point, if your rubber band has twists, how many twists does it have? Does it have how many 2 pi's it has? So think about it, a rubber band attached here, and let's say I'm pointing to the point of starting from omega 0. So I start here, and I'm going here, so I'm coming down here, going back up, coming down here, going back up, going down, and you see that in this case there was no twist. To give you an example of a case where there is a twist, let me just do another variation of this, which is essentially, let's just erase this one. And a lot of times we don't show the upper half, so that's going to be it. So let me show you something else. So let's take a similar system, but it has a little bit more gain, and it comes and essentially goes around it. So if you see, if I start from here, from omega 0, I go up, I go up, and I go up. And this is the first half, and the second half would being the mirror image of that. It would produce a full encirclement of this thing. So this is basically one encirclement. This would produce one right half plane pole. So you can see that we have it. Now, this was interesting, and there was another case. So this is basically the first one obviously was stable. The second was is unstable, the system. And then the third, which is the interesting case, and we saw this last time too, was this conditionally stable systems, where you actually start from here, and you go there, and then you come back, for example, like that. And that corresponds in the Bode plot to a phase response that looks like this. And we have seen circuit examples of those too, where you go below 180, negative 180 degrees, and then you come back up before you hit the unity gain in the magnitude. So something like this. So this, let's say this is negative 180 degrees. The phase goes down, and then you have 2 points at which you have a phase of negative 180 degrees, and then of course you have an additional 180 degrees because of the negative feedback, the polarity of the negative feedback. So in this case, if you actually break the loop, and we talked about this, the signal goes in and comes back exactly in phase. So if you break the loop at some point in your feedback system, let's say this is your A and this is your F, and then you break the feedback loop here, and then you come back in. So if you break this loop at this point and you apply a sine wave here, what comes back is a sine wave in a linear system with exactly the same phase. So if this is the input, this would be what comes back, and larger magnitude, right, at these 2 points. Now, but this, the interesting thing and somewhat counterintuitive thing about this is that this is actually stable. This linear system is stable. And we saw this in the example. You can actually see it. There's no way you can make it oscillate because it's stable as a linear system. And the interesting thing is that this was actually observed in systems, and that's what led to Nyquist criterion to begin with, historically. So that's interesting. So you can actually use this, and you can have even more sophisticated ones. But this counterintuitive one part was good. And then there's a lot of questions about this when you get to real systems, and people say, well, yeah, that may be kind of like a theoretically interesting thing, but in a real system you have nonlinearity, so this system will be always unstable because of nonlinearity, which is not actually true. So there are cases where it can be stable, and there are cases where it cannot be stable. It will not be stable, it will be unstable. And what we'll do today, we'll talk about some of these criteria, so how you determine if something is stable or not using this criterion. It's a more generalized form of criterion. So the question, so let's start it with some sort of a setting of the problem. So now let's imagine that we have a system that has some frequency response, and then on top of that we have a feedback unit, which actually is a memoryless nonlinearity. Well, let's say it's a nonlinearity, not necessarily memoryless. But it doesn't have any dynamics per se. So most of the transfer, so this is a linear system. This is an LTI system with a transfer function. So you break it into an LTI system and a nonlinear system, as shown here. So the question is that, so this is nonlinear and this is LTI. The question is, what can we say about the stability of this system? And the kind of stability we are talking about here is what we call an absolute stability. Absolute stability means that the system will not essentially oscillate. It means that an amplitude of 0 in the absence of an input will be a steady state solution that it converges to. So eventually it goes to an amplitude of 0. It doesn't lead to some sort of an orbit, basically a stable oscillatory motion. So if we start with something like that and want to kind of try to evaluate it, we have to say something about this nonlinearity, for example. So one of the things that you can think about, one way to think about this, is that if you plot f of x as a function of x, right? So this nonlinearity can be something like this in there, and we can even say, let's say, it can be even more complex. It can have hysteresis, essentially memory. It can be time varying, so it can change with time. So t, it can change, and all sorts of things can happen to it. So it can have all sorts of crazy behavior in general. But one thing, one constraint that we would like to apply to this is that we say no matter what happens over all times and all values and all the memories, let's say it is constrained and it's confined, this curve is confined between two lines with two different slopes. Let's say k1 and k2. So this one is essentially the slope is k1, so we show it this way, k1 over 1, and this is the slope of k2, k2 over 1. So essentially, this is confined between those two. And mathematically, the way to write something like this is that we can say f of x is smaller than k1x, greater than or equal, doesn't matter really in this case, k1x and smaller than or equal k2x. So let's say we start with something like that. So that's basically a definition. So we have a nonlinearity in general that can have hysteresis and that kind of thing. It can be time varying. But if that's basically the case, then the question is really what are the constraints and what are the stability criteria for this? So let me ask kind of like you to think about this for a second and think about and see that if you were to come up with some sort of a criterion, what do we think would be a good intuitive criterion for whether or not it is? So we can even make it simple. Forget about the time varying and you forget about the this hysteresis. Let's say you just have something, it doesn't have to be monotonic or anything, but it's just at this point, but just say you have some curve. So we have a curve and intuitively we want to see if we can come up with some sort of a guess of, let's say if you had a curve like this for nonlinearity x, f of x, that had some behavior like that, and it was confined between a k1 and k2. What is a guess? I mean, it doesn't have to be. What would you think? What would be a conjecture, if you will? Anyone wants to venture a guess? Okay. Yeah.
I'm thinking if our system is stable for those two functions, k1x and k2x, maybe our overall function is stable too.
So conjecture number one is that if it's stable, so conjectures, let's say. So stable for f of x equal k1x and f of x equal k2x. You're saying it's stable if it's stable for those two. Okay, so that and the logic for that is that what is the logic for that? What led you to that guess?
Thinking that our system, our feedback is always between those two, and the magnitude. So if the upper bound and lower bound is stable, it's some kind of the worst case. So our overall system should be stable too.
So I see. So you're saying that if it is stable for all of these limits, essentially, right? And if I guess you could also say that if it's stable between these and everything in between, right? Right. So you can say, how about it's a modification to your guess is stable for all k's where k is smaller than k1 and k2, or I guess all kx's, right? So it's stable for all the slopes between. So that's a conjecture. That's a reasonable conjecture. Somebody may come in and say, well, yeah, that is true, but even if it's confined between these, the slope may be larger at some point. In other words, if you think about the small signal gain of this thing, right? So I can create a curve where this slope at this point is greater than even k2, but it still would be confined between these, right? So if you wanted to kind of come up with a conjecture that would kind of like address that, what would we say? How about if we say it's stable for all df dx's between k1 and k2? So in other words, if it's stable for all the possible slopes that you can have, in other words, if it's small signal stable at all points, then it is stable. Right? So that's another conjecture. That's another guess. Well, we are not the first people to come up with either of these conjectures. They actually came up, other people came up with them, and they're actually named after them. So people were not sure if these are true or not. The first one is actually called Iserman conjecture. And then the second one is called Kalman conjecture. So they were conjectured by these people, actually. And the interesting thing is that both of them were proven wrong. There are counterexamples in the literature for both of them. So they conjectured these, and the way to prove to disprove a conjecture is basically all you need is just one counter example. So that's what happened with these, and that was an interesting thing that happened. So then people actually did the derivation of a more accurate, precise. So if we can say both are invalid or rejected conjectures. So what is the correct criterion? What is the way to think about this? It's actually a derivation that we won't do the derivation here. You can find it in most nonlinear control books, essentially, of a criterion, which actually tells you how you can use this. And what happens is that it's interesting because it's graphical. It's actually a generalization of the Nyquist criterion that we developed earlier. So it is called the circle criterion. So basically, if you have this premise, so the correct, and we won't do the proof here, it says that what you need to do, you need to look at the same plane, real and imaginary part of your loop gain, or in this case, basically, we'll assume that all of the dynamics is in the A, so you can think about A of j omega and imaginary part of the A of j omega. So the same kind of plot as you have in the Nyquist. And now on this plot, what you look at is that you identify 2 points. You identify, so we have K1 and K2 that define the nonlinearity. And this criterion is actually valid for all of these like even time varying kinds and all those kind of nonlinear. So you define 2 points. The point 1 over K1, negative 1 over K1, and negative 1 over K2. And then there's a circle that passes through these and has its center on the real axis. So we draw this circle, preferably a nicer one. And this circle essentially is your no-go zone, and it plays the role of the point negative 1 in a standard Nyquist plot. So the way it works is that you actually look at this plot, and you look at, so you remember if you had, we could have these Nyquist plots, right? I mean, so we had something like this. So if you have something like this, there is no encirclement of this circle, and there is no crossing into the circle. So you can, by the circle criterion, this is a stable system with this nonlinearity. And you can see that in the special case of a linear system, where the amount of nonlinearity is basically 1, if you set f of x to 1, the total nonlinearity, you can actually capture the f of x 1, then k1 and k2 would be 1. So these 2 points would both be negative 1. So this circle reduces to a point negative 1, which would become the Nyquist criterion. So you can see that in the special case of a linear system, it is the same thing. So now, let me just show you another example. So how about this? Is this a stable system? No, right? Because what you see here, you have one encirclement of this thing. How about something like this? That is stable, because there's no encirclement or venturing into that region. How about something like this? So now, so this is the interesting thing, which is something that I should have said earlier more accurately, is that this is a sufficient condition for stability. It means that if you don't cross this, you're stable if you don't go into it. But it's not a necessary condition. In other words, it may or may, this system, the fourth system that we talked about, where it goes into this thing, may or may not be stable. So we don't know that for sure that it's stable. But it's a good thing because it's a sufficient criterion in the sense that if you design your system to avoid this, you are guaranteed that it's stable. But it doesn't mean that if you go into it, you're necessarily unstable. You just know that if you avoid it, you will be stable. So it's a stability criterion. It's not necessarily a criterion for instability. So it doesn't tell you if the system is unstable. It tells you if it's stable or not. Or if it guarantees stability. It says if it's stable, I can guarantee stability. That's all it does. So this is actually a pretty useful thing because now you can deal with a broad range of nonlinearities. Actually, you can see it's quite general. So you can imagine all sorts of these nonlinearities that can happen in circuits. And there's a special case of this, by the way, which is basically if K1 is 0. So basically, the nonlinearity is bounded on the in this direction by a flat line, which is the case for some of the nonlinearities. In that case, what this circle criterion does is that essentially K1, actually, yes, no, this should be K2 and this should be K1 because this is going to be closer to the, so K1 in that case becoming smaller and smaller, which means that this point becomes larger and larger. So when K1 becomes 0, this point is going to be where? At negative infinity, which basically turns this circle into what? Into effectively a line, right? So it says if you want to guarantee stability, do not cross this line. For a general nonlinearity. Again, it doesn't necessarily tell you that the system is going to be unstable if you venture into it. But it tells you that if you stay away from this, it's going to be guaranteed to be stable. Now, there are actually there is a variation of this thing, and there are a whole bunch of variations of this thing when you know more about the nonlinearity. So there are certain properties of the nonlinearity that if you know certain properties, then you can make it actually a tighter criterion. So, for example, one example of a variation of this thing, which could be even more useful, is what we call an off-access circle criterion. And many of these were developed by, there's actually a book on this graphical stability measures and criteria by Narendra and I think another co-author. And these techniques, many of them were developed by Narendra at Yale and some of the other people who worked with him, some of his students and colleagues. So anyway, so now off-access circle criterion, it says something else about the nonlinearity. It says that it's actually, now if you know that your nonlinearity is also memoryless, and furthermore, monotonic, then you can actually come up with tighter criteria for this. So how do you describe this? So basically, if you have a nonlinearity that's monotonic, you can say f of x2 minus f of x1 over x2 minus x1 is going to be greater than k1 and smaller than k2. So this describes a memoryless nonlinearity that's confined between two lines with the slopes of k1 and k2. And it's also memoryless and monotonic, meaning that its slope never goes negative, essentially. And it doesn't exceed these levels. So if the slope is limited, confined between these two, what happens is that if you have this kind of nonlinearity, then you can again go to the same graphical representation. You can actually go to the real and imaginary part of your response. And look at that plot. Now, this time, you define the same two points, K1 and K2, on the x-axis. So you can say, I define the same 2 points. So this would be negative 1 over k2, and this would be negative 1 over k1. And you look at your plot. You look at your Nyquist plot, right? So let's say this is there's something like that. Now, according to original circle criterion, you can't guarantee stability for this, right? Because what happens is that if I pass a circle with its center on the x-axis, this is crossing it. So there's no guarantee of stability. But if you know that your nonlinearity is memoryless and monotonic, what it tells you, this new criterion tells you, and again, we are not going to derive it either. It's in a paper by Cho and Narendra, if you're interested. So what happens is that you can actually use any circle, not that goes through the negative 1 over k1 and negative 1 over k2. Not just the one that has its center on the x-axis. So it says if you can find one circle that this curve doesn't cross, then you're good. Then your system is stable. And you can easily see that I can find many. So this is one example, right? And I can find a whole bunch of them, right? I mean, so I can find another one like this. Or there's a large group of circles that this avoids. So you can see that it's a tighter criterion. It requires less. So let me show you another plot, and let's see if we can find something. So if I have something like this, can I find another circle that this avoids? Yes, I can, right? I mean, I can find this bigger circle that goes through here, something like that. Now, but there are certain cases where I can't do that. One obvious example is basically if I kind of go in between them, right? Then there's no circle that I can find that this will avoid. Or if I can make up some strange looking things that come through here, they won't go in between, but they do something really crazy here. They narrow this angle so much that you can't really fit a circle in here that crosses these two. So that's the off-axis circle criterion for nonlinear for memoryless monotonic nonlinearity, which is actually still quite useful because a lot of the electronic nonlinearity that we are dealing with still can be characterized as this memoryless nonlinearity. Now, there's a variation of this also when k1 is 0. When k1 becomes 0, you want to create a circle that basically goes through point k2 and the point negative infinity, which is essentially a very large circle. A circle with a radius, any circle going through those 2 points is going to be very, very large. In fact, it will have a radius of infinity. And what is a circle with a radius of infinity? So let's say we have only point negative 1 over k2. And so what would be a circle with a radius of infinity? It's a straight line, right? So what it says in that case is that if I have a curve like this and if k1 is 0, then what you need to find is that you need to find a line that avoids this graph. Essentially, in this example, this is a line. This is an example of this line, which is essentially that gigantic circle, a very small part of that gigantic circle. Now, is it possible to not be able to do this? Yes. So let me show you a simple example. So if you have something like this. Now, you remember this? This could be, for example, a conditionally stable system from a linear perspective. But now, there's no line you can cross here if k1 is 0. So with a nonlinearity that has a minimum slope of 0, then all of those conditional stable systems will not necessarily be stable. So we can't guarantee stability for any of them, at least using this criterion. However, if your k1, you can limit your k1 so it doesn't become 0, it can become even a small number, then what happens is that there are a lot of cases where you can actually create a situation where this will be stable. So this is a more accurate way of thinking about stability. So these are useful things to think about because they provide a way of analyzing these nonlinearities and thinking about them. And they can be even generalized a little bit more by looking at several different variations of this thing. Even you can use the same concept when k1 and k2, one of them is negative. Oh, so there's a question.
I mean, you are saying that conditional probability in the linear system is stable. Actually, if I have a linear system, I can use conditional stability, excuse me. But in the nonlinear system, it is not guaranteed that my system is...
Well, it depends on the nonlinearity, right? If your nonlinearity, for example, has a K1, so that was a special case, right? But if K1 is non-zero, then you have a circle. You can pass any circle. So there are a lot of those conditionally stable systems are guaranteed to be stable. Let me give you an example. So let's say this is your K1, and this is your negative 1 over K2, right? And let's say, let me just make a curve. So this is negative 1 over, well, this is negative 1 over K2 actually. This is negative 1 over K1. Forget about this for now. So what happens is that, let's look at this. Right? This is conditionally stable linear system, but it's also stable for a monotonic nonlinear, a monotonic memoryless nonlinearity, because I can basically find a circle where this does not cross or encircle.
So there is no circuit or there is no real linear system, and we are modeling our real system with the linear systems. How people make sure that this never happens?
Well, so this is basically the formal way of doing it. You don't want to do empirical stuff and trial and error, which doesn't guarantee anything. It's just you need to kind of like try to kind of think about so many bad situations. But so that's why we need to kind of like look at something like this, because this guarantees, if you can guarantee stability this way, and if you know your nonlinearity, that's useful. Actually, that's kind of gives you some interesting design insights, because, for example, let's say you have a nonlinearity that's purely like this, but it saturates. For example, we've seen the hyperbolic tangents for the bipolar transistor differential pairs, right? The problem with this hyperbolic tangent is that there's an asymptote with a slope of 0, so there's no K1 value greater than 0 that will satisfy this, right? So what happens is that you have to set your K1 to 0, and what it means is that such system will have a K1 0, which basically means that you have a point here that you need to avoid. You have to pass a line with, and it limits a lot of things. So a lot of those conditionally stable systems become unstable. However, if you have, let's say, your nonlinearity, this can be made with a differential pair with bipolars, for example, right? Now, but if you can, in addition to that, you can create a little bit of a linear element, add to it. For example, add resistors. You can have a resistive, you can have it in different ways. You can even have an input resistance or something like that couples to the output or something like some variation. So if you can add a resistor to this network, what happens is that then the total current would be the sum of this and the current of a very small resistor. So this line never saturates at 1. This line will be like this. And then that guarantees a K1 that's greater than 0. And that allows you to create a circle and stabilize it actually in a nonlinear setting and guarantees stability. So that's an example of a design insight that comes from something like that. Okay. So that's a good question. Any other questions? No other questions? Okay. So now there's one more thing I want to actually talk about in this context, because we've talked about this. So we can see that if you think about these questions of oscillation, right? We talked about this Barkhausen criterion, and we see that in this light. We saw that in the light of Eiserman and Kalman conjectures not being true. You see that a lot of those things in nonlinear systems are not necessarily true. So you don't see guaranteed oscillation, or you won't know when you have oscillation or not. In fact, we saw that we can have systems where what comes in and what goes out, what comes out of the loop when you break the loop, is exactly the same phase as what goes in, and it's larger. So you would think that if I put this in, it's going to grow, because what comes back is larger and going to go through this. And that's the wrong image. That's an incorrect intuition about oscillation. Because we saw a clear example of that not being true in the conditionally stable system. So the question is, what is a correct way of doing this? And what is the correct way to think about this? So I'm going to talk about this briefly. And so again, this is a detailed one. I just want to give you a little bit of an insight and a way to think about this. So let's say you have some sort of a feedback system with 2 components. And let's say you are thinking about making something that you want to know when something oscillates, or you want to make something that actually does oscillate. So you basically have no input, and then you have some sort of, I don't know, A of S, F system, and then you want to see what does it take to make this oscillate, or what are the conditions for it. We clearly saw that if something, even as simple as sinusoid, goes in and comes back stronger, it doesn't necessarily guarantee oscillation. So how do we guarantee oscillation? So now the trick to oscillation, think about a sustained, and we're talking about a sustained oscillation. In a more technical, accurate term, we are looking for limit cycles in the system. Stable orbits, basically something that the system goes through. So a stable oscillation in the sense that it produces a stable waveform. It doesn't have to be necessarily sinusoidal, but it's stable. It can be something like that, it can be something like that, but it's stable, it doesn't grow, it doesn't shrink over time, so it stays there, and that's the nature of a reliable oscillator. So what do we need to have? Think about it. For it to be sustained in steady state, what goes in and what comes back should be the same, right? So in general, if you can create a system where there's some waveform going in, and when it comes back in, a periodic waveform with some delay, it can be superimposed on this exactly, then you know that this system can sustain it. Now, this system doesn't actually have to have a sinusoidal waveform. In fact, as an example of one of these counterexample of, you remember you talked about the stability, and it was one of the problem sets that we did, or we are going to be doing, I guess, is that you could have a system where the phase margin, and that homework problem is actually an example of this. You can have a system, and this is where the phase margin never is negative. Your phase never goes below 180, something like that. Or in the Bode plot, you can have a system where the phase never reaches 180, and yet it oscillates with nonlinearity. And there are examples of that in the literature, and you are going to be doing a couple examples to see how these conditions are really just guidelines, unless you really go to some more accurate nonlinear guidelines. So, and these examples can actually be even built in circuits. But so here's the interesting thing: if you have so this in such example, what happens in reality is, well, how is this possible? How is this possible that not at any single frequency you have something that comes back exactly in phase, but you maintain that? The way it works is that individually, the Fourier components of these things never come back in phase. But what happens is that when you add them up, you can actually create a situation that the waveform, the resultant waveform, will have a total phase shift of that much. Which is more accurately, it's a time delay, not a phase shift. It's a time delay, and that really goes back to the differentiation between phase and delay, which are very important and fundamental. So anyway, so that's something to think about, and there are some examples that will, you will see, and details of the discussions. But anyway, so that's it for now, and we'll see you next time.